here there is a convention to take out this conformal Hubble parameter and then write something like that. So again, there is a nth power of the growth factor, and you have this theta tilde nth order solutions which depend on k. I'm then just doing a simple change of variables where I call theta minus h times theta tilde, and then theta tilde is expanded in perturbation theory. So you see, like you can either take this perturbative ansatz and plug it back in these equations, and then formally match all possible orders in perturbation theory, and then you're going to find how the solutions look like. Or, as I said, you can just iterate using the lower order solutions to make, to basically, in the source terms, to compute higher order solutions solving these differential equations. So I'm not going to do any details because you can find all this in the lecture notes and in various places in the literature. But let me just show you the form of these solutions. So it turns out that nth order solution, this delta n of k and theta tilde n of k, can be written as some convolutions in Fourier space in terms of the so-called perturbation theory kernels Fn and Gn. And if you ever study any literature about perturbation theory large-scale structure, for sure you have seen these Fn and Gn kernels appearing all over the place. So what does this formula tell us is that, maybe let me highlight some terms. So first of all, there is an overall conserving momentum delta function, which tells you that the sum of all these momenta which appear under the integral is equal to k, which is the external momentum. So you have a convolution of various linear or initial density fields delta linear, and then they're convolved with some kernels which are a function of momenta. And the way to find these kernels, you can actually find them recursively. And here I'm showing the recursion relations for f and g, where basically Fn kernel, so nth order in perturbation theory, and Gn, which is also nth order in perturbation theory, are written in terms of the lower order perturbation theory kernels. The reason why such recursion relations exist is related to the fact that you can solve these equations of motion by using lower order solutions to calculate higher order solutions. So basically, it is a direct consequence of the fact that you can just iterate, like in solving these equations of motion perturbatively and using lower order solutions in the source to combine them to produce higher order solutions. You can see that indeed, for example, Fn solution combines, for example, lower order Fn minus m and lower order G n minus m with another G n minus m. And this is the consequence of the fact that you have to combine velocity and density with the alpha kernel in the equations of motion, and then two velocities with this beta kernel. So this is just a different manifestation of the fact that you're solving this differential equation perturbatively using this iteration. Okay? So starting from the lowest order, where F1 is 1 and G1 is 1, you can build all higher order perturbation theory kernels using these simple recursion relations. Now, because the way you build them always depends on these alpha and beta kernels that appear in the equations of motion, and these are rational functions of the momenta, then also F and G are going to be some rational functions of momenta. And for example, I'm just going to show you how the second order solution looks like, just to write it explicitly. So the second order solution, which is a function of k and tau, is going to be a convolution of two linear solutions, delta 1 of q1 and delta 1 of q2, convolved through this second order perturbation theory kernel, f2 of q1, q2. And then there is, of course, a delta function which tells you that the sum of these two momenta, of these two linear fluctuations, must be equal to the final momentum of the second order fluctuation. Okay? So is this clear? And in particular, this F2 perturbation theory kernel has the following form. As I said, it is a rational function of momenta, and you see it can be a number, it can be various ratios of Q1 and Q2, and so on and so forth. Okay? Yes. Okay, so how do we get? So the question is like, is this an ansatz or is some form that we should get? This is absolutely not an ansatz. This is something that you can compute as a solution, starting from the equations of motion. If you solve the equations of motion perturbatively, and in particular, what you have to do is the following. Let me maybe be a bit more explicit. So when you let's wait until it comes back. So once you're here, so you see, let us imagine that we want to solve this equation. I'll wait until the plane goes away. So as I said, in the first iteration, you just neglect the second, all second and higher order terms, the only second order terms, and you find the linear solution. This is what you have seen last week, and we also mentioned yesterday. So once you have the linear solution, you can plug the linear solution here, and formally you're going to get a product of two linear solutions, second order in perturbation theory, here as well. And now, since you know the linear solutions, you know the right-hand side of these equations. Now you have to find the second order solution solving this new differential equation. There will be some, you will have to evolve in time this system with a particular source, which is given on the right-hand side of the equation. If you solve this differential equation, you include the time evolution, you're going to find that the final answer is written as a convolution of two linear fields with the F2 kernel. And these numbers in this F2 kernel are not some arbitrary numbers. They exactly follow from time evolution of the source, and you can get them by basically doing the green functions and so on and so forth. You can compute them, and they're not arbitrary numbers. They're fixed numbers, which follow from the fact that we have a particular set of equations of motion, and this is exact in this Einstein-Desitter approximation when omega matter is equal to 1. Okay. Now let me make a comment that. We have to, yes. Physical meaning. Okay, so the question is like, what is the physical meaning of these terms in the F2 kernel? Well, I think that these terms do have some physical meaning. I think that, for example, the constant terms are just telling you. Let me actually say that this constant term, for instance, and this term here, if you look at the structure here, you will have Q1 dot Q2 square over Q1 square Q2 square. This looks like a tidal force. Okay? Well, this looks like a simple number, which means that it has a simple, something which is called the growth, because you're just multiplying delta square with some number. So these two terms are telling you that you have some nonlinear solution, which is proportional to delta square, through basically a simple so-called growth, which is just delta square, and then tidal terms. Tidal, I call this tidal term because it really comes, if you go back to real space, you can see that it comes from something like this, di dj phi squared. So if you have two derivatives of phi, this is the Poisson equation basically delta. So when you have a Laplacian phi, this is delta. So delta square would be this, let's say, constant term. But at same order in derivatives, you may also at second order construct such objects, di dj phi squared. And then if you want to convert this to delta, you will have one inverse Laplacian. And this is why you get this particular structure with Q1 dot Q2 when you go to Fourier space squared divided by Q1 squared Q2 squared. So these two terms are telling you that second order solution is built out of the square of the density fluctuations is the tidal field squared, basically. While this middle term has a different interpretation, and I will say a few words about it in a moment. Okay? Are there any other questions? Okay, so now, so you see, in principle, if you're patient, you can just go use these formulas to generate, like, for example, the cubic kernel will depend on 3 momenta and it will be much more longer and more like tedious thing to get. But in principle, it is some rational function of the moment. And you can just compute any order in perturbation theory. So it's a bit of a mechanical process once, a very simple process once you have these recurrent relations. And what I wanted to say is that this is exact. This type of solutions are exact only for Einstein de Sitter universe, in which we can separate space and time in the equations of motion perfectly. And we have a simple growth factor, which is just the scale factor. And this number in particular depends on this choice. However, it turns out that actually it is a very good approximation to use Einstein de Sitter perturbation theory kernels, even in a generic lambda CDM-like cosmology. This is a bit of a coincidence. There is no some deep explanation for why this is the case. But let me just tell you that what is done usually in practice is that people just replace the growth factors in these formulas. For example, where does the growth factor appear in this formula? Well, it appears in the linear solution. So here this is proportional to the growth factor. So you compute everything like in Einstein de Sitter and then just replace the growth factors with some lambda CDM growth factor. And you will find a very good approximation to the exact solution if you were to solve everything consistently, deviating from Einstein de Sitter. Okay, this is one comment that I wanted to make, such that basically these equations are good enough in practice to do any cosmology. This is important. Now let me say a few words about the properties of these solutions. Okay. So first of all, let me say that I want to study, and this will be important later on, how do these different how do these perturbation theory kernels behave in different limits when some of the momenta are either very small or very large. And so first of all, let me say that if you have this particular momentum configuration, where you have momenta k1 to kn, which are all of the similar size, but then there are there is a momentum q, which is much bigger in magnitude than any of the k's, and of course, it appears with a plus and minus sign in this perturbation theory kernel. Then these perturbation theory kernels scale like k squared over q squared in the limit when q is much bigger than k. Okay, and this is not a coincidence. So first of all, let me say that if you look at this second order solution, this property may not be obvious because there are these constant terms. So you may generically think whatever limit here I take, maybe I will get a constant or something like that. But no, the answer for any of these kernels is going to be such that in this particular limit, things scale like k squared over q squared. This is not a coincidence, and in fact, it comes from the fact that basically this is the consequence of mass and momentum conservation. So the kernels are forced to behave like that because our equations of motion conserve mass and momentum. Okay? Let me maybe illustrate this. So remember that the generic solution, so delta nth order in perturbation theory was some complicated convolution of this Fn. And so, for example, if you have here some, let's say, some momenta which are opposite, Q1 and Q2, and so on, and so a bunch of deltas. So if Q1 is let me put plus, is approximately minus Q2, and these are much bigger than any other Qs, we are really considering what happens when we have some two Fourier modes. So you see we are convolving two Fourier modes which have very high wave numbers. So we are talking about Fourier modes which are fluctuations on very small scales, and we are wondering how these fluctuations from very small scales are affecting the long wavelength part of the solution, which has to do with this typical wave number k. And so, if you want to kind of understand what kind of, basically this is the question, how small scales can affect through these gravitational and nonlinear interactions in the fluid the long wavelength density fluctuation. This is basically the question that you're trying to answer when you're considering this particular momentum configuration. So to find the answer to this question, we can consider a simple exercise where we imagine that there is some region of space of some radius r, and we're going to imagine that we have two density fields, so delta A and delta B, which are such that they're equal outside this region of space r, but inside this region, let's say we move particles around and we change a little bit the positions of these particles, however, in a way which preserves mass and momentum. Okay? So this is very important. So these two fields are identical outside this region, and they're different inside this region, but they're different in a way which preserves such that the mass and momentum of this region is always the same. Okay? So if I compute the difference, delta A minus delta B, and I consider a Fourier mode k of this difference, I'm going to find that this is equal to the integral d3x. Of course, x here is inside this region, because outside this region, these two fields are identical, so everything cancels. And then I have delta A of x minus delta B of x, all multiplied e to the minus ik x. Okay? And now, if I consider the wave numbers or Fourier modes or like wavelengths of fluctuation, which are much bigger than this region r, I am in the limit when kr is much less than 1. Okay? If I want to consider some very long wavelength fluctuations, and I'm wondering how these very long wavelength fluctuations of this field are modified by the fact that I did some small-scale transformation inside this region. So in this limit, I can expand this exponent, because x is always smaller than r, since I'm integrating inside the sphere. So basically, I can write this like 1 minus ikx, and there will be terms of order k squared, x squared. Sorry. And now, if I ask myself, for example, this first term, this 1, what is it going to give me when I integrate over d3x? Well, the integral of a d3x of this density contrast is just, or a rho if you want, is just going to be, the density contrast is 0, but the total rho will be just equal to the mass of the particles in this region. So therefore, this one doesn't play any role since the mass is conserved. I'm not going to get any contribution, and there will be exact cancellation between these two terms. Similarly, the second term just measures the position of the center of mass of this region, because it is x times delta, or rho, which is like basically calculating the center of mass of particles in the distribution A and distribution B. And if the momentum is conserved, the center of mass will be also the same. And so, therefore, I'm going to also drop the second term. And the only first non-trivial term that can appear is proportional to k squared. So basically, this means that the whole answer goes like k squared. And so what this means is that if you consider some small scale fluctuations, the only way that they can affect large scales is in a way which is suppressed by k squared. Okay? And so we are seeing this in these perturbation theory kernels. this is a general argument as long as the mass momentum is conserved. Since our perturbation theory equations are conserving mass and momentum, then also perturbation theory kernels have to satisfy this property. Okay? So this is the property number one, which will become important later on. And the property number two, which is also rather important, and I'm coming back to your question about what is the physical meaning of this middle term in the F2 kernel. So the property number two is the following, that if one of these momenta in the perturbation theory kernels is much smaller than the other momenta, then the perturbation theory kernel scales in this way. It is basically proportional to the one, so basically the large momenta k divided by the small momentum q. So now this is also a very peculiar type of, let me for example remind you that in the F2 kernel, we had 5/7 plus there was a term which was q1 dot q2 over q1 q2 and then the tidal piece, which was 2/7 q1 dot q2 squared over q1 squared q2 squared. Okay. So we said that this was growth, these were tides. These are simple gravitational nonlinearities that we understand very well. But now, if I make, for example, q1 much smaller than q2, I can see, for example, that this term is going to behave like q1 dot q2 over q2 squared. Sorry, I think that I'm getting this wrong. What I really want then is to make q1 much larger than q2. So in the Q, and this happens generically for any perturbation theory kernel. I'm just showing you the example of F2, where does this term appear. Now, you see when Q2 goes to 0, basically, compared to Q1, this looks to be divergent. Okay? And that is a very peculiar feature of the perturbation theory kernel. They seem to have this, we would say, infrared divergency, because it has to do with the very small wave numbers or very large wavelengths. Okay? Now, what is the physical meaning of this term? Well, actually, if you go back to the equations of motion and trace where does this come from, you're going to discover that these terms are generated by the types of nonlinearities in which you have basically the gravitational potential, the gradient of the gravitational potential multiplying the derivative of delta. Okay? So essentially, this is what this term is. And indeed, if I take this formula in real space and I go to Fourier space, so first of all, for example, I can write this as delta times the gradient of delta using Poisson equation. And then, clearly, going to Fourier space, I'm going to get exactly this momentum structure. So you see, for example, this Q1 is going to be one derivative acting on delta, and then this particular structure Q2 divided by Q2 squared is going to come from this inverse Laplacian here. Okay? So this is really going to give me Q1 dot Q2 over Q2 squared of delta Q1, delta Q2. Now, what is this nonlinearity? Well, this nonlinearity actually is something that has to do with a particular feature of gravity, that if you have a very long wavelength density fluctuations, they're going to generate some homogeneous gravitational potential, which is gradient phi, and then some short scale modes are going to fall in this gravitational potential phi, and therefore they're going to be displaced. They're going to be displaced by a certain amount proportional to the gradient phi, and this term here is just the leading order in perturbation theory term of this displacement. So if you want, really what schematically happens is that I have to take delta and displace it from its original position x to some new position, which is proportional to the basically gravitational acceleration times some time squared. So take this formula, the quotation marks, just to get the dimensions right. Okay, so in some cosmic time, you move at a certain distance. And now, if I do Taylor expansion of this, I will get delta of x plus the next term is going to be proportional to exactly our second order term and so on. So in perturbation theory, these type of terms, which appear to have this infrared divergence, are related to this displacement by small scales by the long wavelength modes, which produce some homogeneous gravitational fields where things move, and they can move by a large amount. Okay. Now, since this looks like a divergence, the question is like, should I be worried about it? Is this something to be worried about? And the answer is no. You should not be worried about anything. It is what it is. But you should be careful about it. In fact, it will play a very important role in what I'm going to say, in particular tomorrow. Okay? No. This phi, you remember, was just the gravitational potential. But you don't. Maybe you're thinking about relativistic. Are you talking about the inflaton and relativistic formula, or? You should be careful because, for example, well, I will just say, this phi really corresponds to the gravitational potential associated to density fluctuation. Density fluctuations grow in our universe, in the method domination. The growth of phi is constant. So you should be careful that there is like, but nevertheless, the fact that phi is constant doesn't mean much because the derivatives of phi can grow, special derivatives, and delta indeed grows. So, sorry, Dan? Yes, that delta is like a local overdensity, density contrast perturbation, and phi is associated gravitational potential through the usual Poisson equation. So this is what it is. Anyway, I just wanted to say here that this particular, and we will come back to this tomorrow, this particular apparent infrared divergence, it has a very important role, and it has some physical meaning for the BAO peak, and it comes really from this type of terms in the gravitational nonlinearities, where we're displacing small scales, moving them far away because they're in a free fall in the long wavelength background of some long wavelength density. All right, so okay, so I think that this is what I wanted to say about the properties of these kernels. And now I want to show you, finally, so what we did now is I wrote down how this perturbative solution looks like once you solve these perturbation theory equations. I discussed a little bit what are the properties of these perturbation theory kernels and explained what does it have to do with the mass momentum conservation, the property number 1, and the property number 2, which has to do with these large displacements and the free fall in the background of like some long wavelength density fluctuation. And now I would like to show you how to actually compute nonlinear correlation functions using these perturbative solutions. Okay. So as we wrote like a few slides earlier, schematically, the nonlinear solution that we are after is basically sum of different orders in perturbation theory. You have the linear term plus second order term plus third order term and so on. And schematically, you can represent this, you can do it in various different ways, but here I'm imagining that in some sense time goes in this direction, and I have a linear solution, which basically is a free evolution. This Fourier mode is independent of everything else, and it just remains always the same. It grows with the growth factor. Then you may have second order solution where you combine two different Fourier modes in the initial conditions at some point through this perturbation kernel F2 to give you a second order solution. The third order solution is like a combination of three different Fourier modes which combine to through F3 to give you delta of k at third order, and so on and so forth. Okay. And once you have this solution, and each of these little diagrams, these long expressions we had in the previous slides, then you can just compute the correlation functions. And Cora, for example, this morning mentioned that the field becomes non-Gaussian because of the nonlinear evolution. Let's see this explicitly. So let us do one of the simplest computations you can imagine, which is the computation of the bispectrum, which is a 3-point function of the nonlinear density field. Okay? So let me do this step by step, just to give you a simple illustration of how does it work, and then you can easily do this yourself for other possible observables that you want to consider. So let me write it down again. Now, in principle, we should expand every of these fields in perturbative series. And here I want to consider only the lowest order terms in perturbation theory. So at lowest order in perturbation theory, I can consider this field to be the linear field, this one also to be the linear field, and this one to be the second order solution. Okay, so certainly one contribution at lowest order in perturbation theory is this one. But however, I can make this choice of considering second order solution here or here. Okay, there are the three possible options where to put the second order field. And so therefore, I have two other expressions, which I'm just going to denote like this. They're going to be identical, except that you will have to permute k's, because everything that we say here about k3 will equally apply to k2 and k1. So you don't have to write them explicitly. Okay, so then what is this expectation value? Well, to find it, I have to basically write the following thing. I have to compute the expectation value of delta 1 of k1, delta 1 of k2. And then here, I have to plug the expression for the second order solution. So remember, this expression was two integrals over two Fourier modes q1 and q2. There was the momentum conserving delta function of k3 minus q1 minus q2. And then delta of q1, delta of q2. Okay? So this is what we have to compute. Of course, these two fields are linear fields. And now, sorry, there is the most important thing missing, which is f2 of q1 and q2. So now, this momentum integral, delta function, this f2, this is not something that cares about this expectation value. So this expectation value acts only on this field delta, and Cora already told you this morning that for the field which is a Gaussian field, which we are going to assume the linear field to be, this kind of expectation values can be easily computed in terms of only the power spectrum. So you remember that when you have the Gaussian field like that, you just have to consider all possible weak contractions. And in this case, there are like three possible weak contractions. For example, you can contract these two fields. But then this is bad, because if you want to consider momentum configuration where k1 and k2 are different, this is going to vanish. So we are not going to include that one. And the other weak contractions is when we contract some of these deltas here with those fields outside. Okay? So for example, one possible choice is to do the contraction of this thing with this guy here, and this one with this one here. Or the other option is the other way around. So these are the only two possibilities. And it turns out that these two possibilities are going to give you identical answer. Okay? So if you do that, in each of these contractions, you're going to get one simple power spectrum, and, sorry, the two-point function in Fourier space, which is going to give you, for example, this contraction here will give you 2 pi cube Dirac delta of k1 plus q1. And this other construction is going to give you 2 pi cube Dirac delta of K2 plus Q2. And of course, here you're going to have the power spectrum of K1 and the power spectrum of K2. So at the end of the day, you're going to end up with 3 delta functions and 2 momentum integrals. And the answer for this thing is going to be 2 pi cube Dirac delta. This you can check yourself, K1 plus K2 plus K3. And then we are going to have 2 times F2 of K1, K2, P of K1, P of K2, and then plus 2 permutations. So you can see that the nonlinear 3-point function is not 0 for the nonlinear field. For the Gaussian field, it would be 0, of course. For the nonlinear field, it is not 0. And at leading order in perturbation theory, it has the generic structure you expect. There is an overall delta function telling you that all these 3 momenta have to sum up to 0. And then the leading perturbation theory result for the bispectrum is just given in terms of these simple expressions, which has like the product of 2 power spectra. Okay? Is this clear? Yes. Yes, the question is like, this is just true for the Gaussian fields. For the Gaussian fields in the initial conditions, yes. If you have some additional non-Gaussianity in the initial conditions, then there will be a term here which doesn't vanish, which is a linear, and this is just the primordial non-Gaussianity part. So if you had some primordial non-Gaussianity in your dark matter simulation, let's say, then the total bispectrum will be given by one term which has to do with the nonlinear evolution, and there will be another term given by the linear evolution of the primordial non-Gaussian part. Any other questions? Okay. Now, let me point out here that the thing that we discussed earlier about this, like something that looks like some infrared divergence, can also appear a little bit puzzling in the 3-point function. Consider, for example, the case in which K1 is much smaller than K2 or K3. This is the so-called squeezed bispectrum. So if you look at this momentum configuration, you will see, for example, that among these permutations, there are F2 kernels which are going to appear to go like 1 over K1 because of this particular term that we discussed in the previous slide. Let me just finish this. So it would seem that there are terms like that. So let's say K1 dot K2 over K1 squared, for example, which seem to be going to infinity when K1 goes to 0. However, if you look a little bit more carefully, you will see that these terms always cancel, because they will appear in 2 out of these 3 different permutations, and they will appear with the opposite sign, so that actually, this is naively they're there, however they cancel. So we are never sensitive to these large infrared contributions in correlation functions. This is a general lesson, and I'm going to come back to that on Thursday to discuss it in more detail because it's important. But for the time being, let me just mention it here. So I don't know if you see how it happens. Basically, the way that it happens is there are 3 permutations. You will find one kernel which has this particular structure. There will be another one where you have K1 dot K3 over K1 squared. And when you sum them up, because K2 is forced to be basically minus K3 in this particular limit, then they're going to cancel exactly. And this is always going to be the case. And this is a little hint for something like deeper or like more important and more general that I'm going to discuss on Thursday. So the question. Oh, like I think that this bispectrum is defined in any configuration of the momenta. This particular limit is the limit in which you're considering 1 very long well fluctuations correlated with the 2 small scale fluctuations. And I told you that in the nonlinear evolution, in this configuration, you have this large displacement, that the long wavelength mode can displace small scales far away. And I'm just trying to see whether I can see it in the bispectrum. And in fact, I do not. These things cancel. Essentially, they cancel because I have two small scale fluctuations, and they're displaced by the same amount, by the long wavelength field. This is going to, I'll come back a little bit to tell you a bit more about this on Thursday. And in general, you may be puzzled about this. Like, do I have some infrared divergence in my correlation function? That would be very interesting to know. And the answer is no. Okay, so this was the bispectrum. And let me see. I'm running out of time. Amazing. So now let me very briefly tell you that you can compute in this way any observable you want, really. So let me just, well, I can maybe skip this. So you can like compute any observable you want, and in particular, now we can look at our favorite observable in cosmology, which is the nonlinear power spectrum. And then you can play the same game. You can expand the nonlinear field in powers of delta. Of course, at leading order, the result is equal to the linear power spectrum, which is just a correlation of two linear fields. But then at higher orders in perturbation theory, you have additional terms. And here I'm writing all possible terms which are basically next order in perturbation theory. So that there will be no terms which have linear and quadratic solution because they have three initial fields, and the three-point function vanishes for the Gaussian fields. So it must be of the order of the four initial fields, and you can have either two second-order solutions or one linear and one cubic solution. They're the same order in perturbation theory. And then you can simply go here and I think that I will skip the details. You can again do the very same exercise as we did for the bispectrum, playing with these contractions, being careful about delta functions, and so on and so forth. I can leave it as an exercise for you to show that actually you basically let me maybe say that these two types of the contributions, one of them is two second-order solutions. One is a linear and cubic. I'm going to call P22 and P13 contributions to the one-loop power spectrum. And in terms of diagrams, they have different representations. So for example, P22 really comes from taking the expectation value of two second-order solutions. So you have to do two contractions, something like that. And each one of them gives you the power spectrum. So sometimes we represent this more abstractly as a diagram which is like that. And P13 is a contraction of a single linear mode with the cubic solution. In that case, you will have one contraction with external leg, and there will be another contraction like that. And this diagram is sometimes drawn like this. So there is one internal line here, and then there is one external line here. Anyhow, this diagrammatic representation is just some convenient tool to draw pictures and convey information quickly. But the formulas for these two contributions are not very difficult to find. And indeed, as you expect, and this is wrong, the 2-2 contribution depends on the square of the F2 kernel because we have two second-order solutions. This factor of 2 here appears because we are going to have two non-trivial contractions. And then we have two power spectra that we are integrating over. While P13 contribution depends, of course, on the cubic kernel F3. And you see that in the cubic kernel F3, it is very important that we have this Q and minus Q. And this is consequence of the fact that we are doing these contractions here, okay? So we are contracting two internal lines, and they're going to have opposite momenta in this expression. So these are some expressions that you can basically compute numerically. If I give you the linear power spectrum, let me maybe specify that all these are, of course, linear spectra. So if I give you the linear power spectrum and I give you this form of perturbation theory kernels, you can solve these integrals numerically, and you can compute what are the nonlinear corrections to the linear power spectrum. Okay? One important maybe point to keep in mind is that because these nonlinear contributions are proportional to the power spectrum square, they scale like the growth factor to the 4th power, unlike the linear power spectrum, which grows only as the growth factor square. And this tells you that if you go back in time, when the growth factor is smaller, these nonlinear contributions disappear faster than the linear theory. This is why we say that if you go back in time or you go to high redshifts, the nonlinearities are less important compared to the redshift 0. Okay, so here I'm showing basically the plot where you can see various contributions. I don't know if you can see it well, but for example, this is the linear theory. And as you imagine, on very large scales, the linear theory is much bigger than the nonlinear corrections, and it's a very good approximation to the full answer. And then when you compute individual diagrams P1, P22, and P13, and you sum them up, you get this P1 loop. And also, as you expect, this P1 loop is relatively small on scales which are mildly nonlinear, and eventually it becomes the same size as the linear theory around the nonlinear scale, which is approximately, I told you, 0.3 H inverse megaparsec at redshift 0. I think this plot was made for a slightly higher redshift, 0.6 or something like that, but it doesn't matter. Roughly speaking, around this scale, the loop contributions become as big as the linear theory, and this is naturally the place where perturbation theory breaks down. Yes? There will be, yes, there will be. I'll discuss this in detail like a little bit later on. Well, let me come back to that in a bit. So, okay, so now that we have these solutions and we can just numerically compute how this nonlinear power spectrum looks like, it is time to confront this computation with reality. Okay, so let me now show you how does this look like when you compare it to the reality. And as you may imagine, no, maybe you don't imagine, but I can tell you it looks terrible. Like whatever we computed doesn't work. Okay. So now let me guide you through these two plots. So what is shown, let us first take a look at the right-hand side. So what is shown here is the ratio of the total of the nonlinear power spectrum to the linear theory. Okay. So on very large scales, this ratio is basically equal to 1. So we have that the full nonlinear theory is equal to the linear theory. And then, for example, if you take a look, of course, for the linear theory, this is just a straight line. The ratio is trivially equal to 1. If you take a look at simulations, which are these black dots, then we see that the nonlinear power spectrum, as you know, is larger than the linear theory as you go to high K. And this is what you see in these data points. And then what is shown here is what happens when you add to the linear theory this one loop standard perturbation theory power spectrum that we just computed, which is the sum of P22 and P13 contributions. So if you do the one loop calculation, here, of course, you don't see much of a difference compared to the linear theory because nonlinear equations are small. But as you go to smaller scales, you see that this contribution doesn't fit the data. Okay? Now, you may think, well, I maybe didn't do computation which is precise enough, and perhaps if I go to higher orders in perturbation theory and include more terms, things will get better. And you can go on and compute, for example, the two-loop contribution, which is like next to leading order in perturbation theory. Well, you will have to go to the 5th order in like a density field. And what you will find then is that, again, it doesn't look good. So we are not able to get the correct behavior of the nonlinear power spectrum on these small scales. Whatever we did fails. Okay? Another mode of failure is that if you take, basically, here, you take the linear theory plus this P1 loop that we computed, and you take the total nonlinear power spectrum and do the Fourier transform to compute the two-point correlation function, what you're going to find is this plot on the left, where in the two-point correlation function, again, you have some data points. The black solid line is the linear theory. I told you yesterday that this is the baryon acoustic peak. This is the feature, which is like a single peak, which is a Fourier transform of the BAO wiggles in the power spectrum. And you can see that the linear theory acoustic feature gets broadened in the nonlinear solution. The points are they have a much broader feature. There is a damping of the BAO peak. However, your theoretical calculation predicts a line which really doesn't look like anything. It has like these two peaks, so clearly it doesn't go through data points. Okay? So whatever we did so far is wrong, not only on small scales. So you see, when you go to high K, you're going to small scales, and things do not work, but also these formulas that we were using so far for the nonlinear matter power spectrum are completely wrong on very large scales. This is a 100 megaparsec scale. So they cannot properly describe the nonlinear BAO peak. So 2 days of lectures are wasted, and this is the answer. It looks very bad. Now the question is, of course, what went wrong? And for the rest of the lectures, I'm going to try to explain what actually goes wrong in this usual naive way of doing things, and how to fix it. Okay. So by the time we take a look at the correct answer, all of these issues are going to go away, and the curves will perfectly nicely go through the data points. So we will be very happy. Okay. Are there any questions about this? Is it clear what is plotted here? First of all, are you surprised to see this? Did you expect it to work? Probably not, because I told you that you're doing something wrong. But yeah. Still, it is always like a bit shocking to see this. So now we can ask what went wrong. And actually, this was like the cause of a considerably large debate in the participation theory community. And there are several options. One option is that the equations of motion that we were using from the beginning were wrong, and that is option number A. And then the option number one, number two, it may be that the equations were correct, but somehow the solution that we found was not really complete in some sense. Okay. So it turns out that both of these things are correct. Actually, the solution is incomplete in some sense, and also the equations of motion are wrong. Today, I wanted to tell you a bit about why the equations of motion are wrong, and probably I will not have time. We will start, but probably will again have to finish tomorrow. And I will also wanted to tell you tomorrow about why this solution is incomplete, and this is going to have to do with this. Just to give you maybe a hint, this is going to have to do with these large infrared contributions in this particular soft limit of perturbation theory kernels, because you have something which is very large when momenta are becoming small. People thought that perhaps you should not miss these terms, you should somehow include them, and that in fact this is true. But there was a lot of confusion between how this is related to the first problem, and there was a lot of back and forth and some attempts to resolve both of these issues by including more terms, doing some summation, stuff like that. That really didn't work. Okay, I'm going to tell you what is the real resolution at the end of the day. But anyway, this was something that was puzzling people for a long time. And luckily now we know what is the answer, and I'm going to tell it to you by the end of these lectures. But for today, we are going to start answering or addressing the first problem, that actually our equations of motion that we started with were wrong. Okay? They were not consistent. They were not allowing us to actually find the right answer. Okay? So now the question then is, what are the correct equations of motion, and how do we discover them? It may not come as a complete surprise that we are getting something which is not entirely right, because I just postulated that dark matter behaves as an ideal pressureless fluid, but we never justified this. We never derived that this is really the case. And we just use this by some analogy, maybe with what we do in the CMB, where there are no these issues, or like, I don't know, some vague intuition, but there was never a rigorous justification for why this is the case. Okay? So indeed, if you take a look at the correct equations of motion for the dark matter, you will actually see that the right way to describe it fundamentally, and the way that numerical simulations solve this problem, is to have a bunch of particles which all interact to each other through this Newtonian gravity. Okay, and so and they're basically on a computer. This is actually what you're solving. But there is a way to rewrite this. If you just smooth these dark matter particles and represent them as a field, there is a way to rewrite it in terms of this so-called collisionless Boltzmann equation, or Vlasov equation, which is the equation of motion for the full phase space distribution function, which depends on the position, depends on all possible momenta of various particles in a given position in space, and depends on time. Okay? It's a very complicated object that has the full phase space information about your system. And then it has the following equations of motion, where this phi is the gravitational potential induced by the distribution of matter in space. Okay? So this is really what n-body simulations solve, if you want. So they're not solving a fluid equation. They're solving the full Boltzmann equation. Okay? Following essentially every individual particle as it evolves in this complicated system. So where does the fluid, the idea about fluid come from then? And now we saw that actually in practice it doesn't work, but if you take a look at this, since there is no collisional integral on the right-hand side, this system is collisionless, and we know that dark matter particles can go through each other without ever interacting with each other, right? So at that point, we can even become desperate, because we know that collisionless systems do not have a fluid description. The fluid description requires that you have like a fluid element where all the particles are moving together, and there are no multiple streams. You have a single stream approximation, and so on and so forth. And you need some interactions, you need some collisions to achieve this fluid approximation. However, the dark matter particles never interact with each other. So how come that we can even consider it to be a fluid? Okay, this is one question that now we should ask ourselves. So we started saying, oh, this is some simple pressureless ideal fluid, but now we see that if we think about it, actually it can never become a fluid. It will, but in a non-trivial way. Okay, so what to do then? Okay, the system is collisionless. For example, in cosmology, there is an example, and I don't know if Julien talked about it, but neutrinos, for example, in the early universe, are not treated as a fluid. When you're solving CMB, you don't treat neutrinos as yet another fluid. You have to solve the full Boltzmann hierarchy. You have to follow all the moments of their distribution, because indeed they're streaming through each other. They're not behaving like a fluid. And dark matter formally is the same thing. So what should we do about it? Okay. So not all hope is lost. And since I'm running out of time, I don't know if I will be able to. I don't know what is the best strategy, but let me tell you what is the intuition for why eventually some fluid-like description is not hopeless, and actually we can do it. And there are basically two reasons for why dark matter, at the end of the day, will have a fluid-like description, just not the one that we were using at the beginning of these lectures. Okay? So first of all, even though the dark matter is a collisionless system, which means that formally the mean free path is infinite. The particles can travel as far as they want without interacting with another particle. So despite this being formally true, in our universe, in reality, there is some mean free path. So the mean free path is set by the age of the universe. So it is true that formally the dark matter particles can go as far as they want, but in the finite age of the universe, they cannot go very far. In fact, if you compute, if you imagine the typical velocity of dark matter particles, is of the order of 100 kilometers per second, then the distance that they move within the age of the universe is of the order of a few megaparsecs. They cannot move much further than that because they're not very fast. Unlike neutrinos, which are moving very fast, almost with the speed of light, and they can free stream, and they cannot be treated as a fluid, dark matter particles are very slow. They start with a zero initial velocity, and all their velocity is gained due to gravitational interactions and nonlinearities, and so therefore they're moving slowly, and they're not moving far away. So this is something that gives you, in some sense, some effective notion of the mean free path. And on scales larger than these few megaparsecs, basically the dark matter particles are moving coherently. And so this is why the fluid description eventually will be possible. And the property number 2, which is different than the usual collisionless system that you may imagine, like some particles in the box, is that the dark matter forms halos. So it's not true that dark matter particles just come together and go through each other. They virialize, they form dark matter halos, and somehow effectively this glues them together. And this is another reason why this simple intuition about a collisionless system where everybody streams through each other does not apply here. It doesn't apply because we have gravity, which is very important in the dynamics of this system. And again, we know that the formation of dark matter halos has to do with a similar scale. So everything becomes nonlinear, typically also at a few megaparsecs. So we see that these few megaparsecs in Fourier space is roughly 0.3 or 0.5 or whatever you want to call it, age over inverse megaparsec. And this is exactly the nonlinear scale that I was mentioning at the beginning. So what is going to happen, and I think that we will discuss this in detail tomorrow, because there is no time now, is that it will be possible to justify rigorously some form of the fluid-like description on scales larger than these few megaparsecs. On scales smaller than a few megaparsecs, there is no fluid description for dark matter, and one has to do the full problem. But on scales larger than these few megaparsecs, there will be a fluid-like description, except that we will have to be careful about how do we exactly derive equations of motion for this fluid. This is not going to be ideal fluid anymore. It will have some non-trivial stress energy tensor on the right-hand side of the Euler equation. And we will have to be a little bit careful about how we treat that, the whole system. But what is going to happen at the end of the day is that there will be a fluid-like equations of motion. And therefore, we are just going to have to a little bit to correct what we already computed in order to match everything to the basically numerical simulations or this nonlinear data. Okay. Now this idea of starting with this microscopic description and then deriving these equations of motion for density fluctuation and the velocity divergence, which are fluid-like quantities, is basically what is this effective field theory of large-scale structure. So this is an approach in which we are going to smooth or an average over the small-scale fluctuations, consider only the long wavelength fields, and then find the equations of motion for these long wavelength fields. And even though that the complete UV theory is very complicated. It's some collisionless system which is self-gravitating. The long wavelength behavior of this system, when you consider fluctuations on very long wavelengths, large scales, is going to be fluid-like. It will be very universal. And indeed, this is very similar to what happens in other areas of physics. For example, just think about hydrodynamics. So people were able to write down equations of hydrodynamics before they even knew that atoms exist. Okay? So, and even there, if you want to describe everything microscopically, things get very complicated. But when you go on scales which are larger than the mean free path in the fluid description is valid, and the equations of motion for the long wavelength degrees of freedom simplify significantly. The same thing will be true for dark matter. Even though this system is a bit more complicated and strange than the usual fluids that we find in the laboratory, still a fluid description will exist. And tomorrow, I'm just going to briefly tell you about it. We will see how actually one of the problems with this disagreement with simulations is getting resolved. And then I will move on and give you a little bit more explanations for what happens with the BAO peak, and comment briefly on how do we apply the same methods to basically real galaxies in redshift space, in full glory, things related to the real observational data. Okay, I'll stop here and take questions. Okay, so let me repeat the question. The question was like, we came to the conclusion that somehow we have to add something, not really collisions, we have to add something on the right-hand side of the Euler equation. We will see what it is. And the question is, like, does it mean that dark matter interacts with some other interaction other than gravity? Well, the answer is no. It can interact only gravitationally, but you see the gravitational interactions are very non-trivial because they form bounded objects like dark matter halos. Dark matter halos can interact with each other and form another bound structures and so on and so forth. So this fact that the dark matter on small scales, the dark matter cannot just like free stream and run away and go across cosmological distances in the age of the universe is very important to allow for this fluid-like description. So we are not adding any physical interactions of dark matter. We are really just taking into account that we can, whatever happens on small scales, no matter how complicated it is bounded either in dark matter halos or in small, a few megaparsec motions of dark matter particles. On large scales, from the large scale point of view, this will behave like a fluid. So we're just going to exploit this fact. However, because you have some non-trivial thing happening on small scale, this is going to impact large scales. But, for example, by the arguments I just showed about momentum conservation, this impact will not be very large. It will go like k squared again. No, these are not. Exactly. This is a very peculiar system. It's not a collisional intuitive sense. Yeah. Still, the system is fully collisionless, but it can develop these non-trivial solutions, and then on certain scales it will behave like a fluid, even though formally it is not. The question is, like, can we add neutrinos to this description? I think that no, because not in a trivial way, because neutrinos are very fast. So in the age of the universe, they cross very large distances. And so their effective mean free path is huge. It's a free streaming scale. And so neutrinos will behave like a fluid on scales much larger than the pre-string scales, but this is bigger than the size of the universe. So if you want to treat neutrinos together with dark matter, you have to, for the neutrinos, you still have to basically solve the full Boltzmann equation. However, one thing that simplifies your life in that case is that neutrinos are a very small perturbation on top of the dark matter, and basically you can solve, instead of solving the full coupled system, you can in some sense perturb not only in the fluctuations of dark matter, but also in the amount of neutrinos, and in some sense solve how neutrinos move or how the distribution function evolves in the fixed dark matter distribution, and then this simplifies calculation a bit. It's a very complicated problem, but neutrinos are different. They have a long Mifri path. Yes?
So the way you presented it, you realize all this problem after the disagreement in the simulation. Is that the way it happened historically, and when did it happen?
My feeling is that historically, and if you go back and look at all papers, people were historically always starting with the collisionless Boltzmann equation. Then they would say, okay, let us now write down a few moments, and you will get the usual continuity and Euler equation. On the right-hand side of the Euler equation, there will be, we'll see some of it tomorrow, it will be like this anisotropic stress tensor. But then they will say, if you measure this stress tensor in simulation, it's very small. But you can just neglect it. And so we are going to use like ideal pressureless fluid as a description of dark matter. And then when things didn't work in simulation, they tried to solve it in various ways for a long time before this EFT logic came to be. So I think that basically what EFT actually brought historically was to actually discover a systematic way to find the correct equations of motions you want to solve. But I think that it was not a trivial observation. It took some time for people to understand that there is a problem. There were various other solutions proposed before GFT. Yes?
When you consider bionic matter into the simulation, what's the difference in the electricity or the constant density? Because if you consider bionic matter, you have to consider the momentum evolution.
Yes. So the question is like how the picture changes if we have to include baryons and baryonic matter, because for example there we know that there is a collisional term. It's not collisionless. Let me give a fast answer. I mean, one has to take a look at it thoroughly. But what actually happens is that if you think about adding baryons, first of all, baryons are only 20% of the matter component. So they're, again, relatively small perturbation on top of dark matter. And the second thing, all baryonic processes, which are non-gravitational, that has to do with electromagnetic interaction and so on and so forth, are active at most at the 1 megaparsec scale. You cannot imagine that baryons can explode and spread across the entire universe. Okay? They always also remain localized. Even though like a gas can be heated and supernova can explode, still everything remains in the same dark matter halo. So from the point of view of being on large scales, baryons as well, even though they have even more complicated short-scale physics, will behave effectively like the same fluid as dark matter. So a very good approximation, which is basically as good as we're ever going to need, we can treat dark matter plus baryons together as a single fluid, essentially. And the corrections to this picture are very small and probably hardly observable. So I think that people have been studying this in detail, but I think that we can still think of it in the same way. It's a different story for the tracers, for galaxies, and we're going to see tomorrow. Their situation is different. There are many, many differences. But there we're really talking about the density field of discrete tracers, not about the field of total matter, which is dark matter plus baryons.